actually, when we started it, we mentioned that it is known from practice, from a real life experience. But what I show just now, this result we can prove theoretically. So this result is true in our theory. So it is law of large numbers. For the relative frequency. Strong law of large numbers for relative frequency. It means that the sequence of relative frequencies converges to the probability. It's an old result. It is proved by Bernoulli. It's an old result. The sequence of relative frequencies converges to the probability. So how to get this result from the law of large numbers? Law of large numbers, the general law of large numbers. So let A be an event. Repeat our n times. For example, we repeat tossing a coin several times. We repeat rolling a die several times, and so on. Let our random variable xn, xi be 1 or 0. Why? If A occurs in the ith repetition, and 0 if I bar, that is the opposite event in the as repetition. So for example, in the case of head or tail, first is head, second tail, head, head, tail, 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 head, 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 head. Here we write x1 is equal to 1, x2 is equal to 0, x3 is equal to 1, x4 is equal to 1, x5 is equal to 0, x6 is equal to 0, and so on. So, you see, if we add x1 plus x2 plus xn is the number of heads here. So it is favorable, the number of favorable cases. Therefore, if we divide by n, no, not favorable. It is not good. Not good. It is not good. It is the number of heads over n, number of heads over n. So it is the relative frequency. Relative frequency. So it is the relative frequency. But by the law of large number, this part goes to n. What is n? n is the expectation. But what is the expectation here? The expectation of xi, 1 times the probability of this event, plus 0 times the probability of the opposite event. So it is the probability of A. So it is the probability of A. In this special case, m is the probability of A. So the relative frequency of A goes to the probability of A. So our general law of large numbers contains a special case, an important special case, which is called Bernoulli law of large numbers, and it is the following. The sequence of relative frequencies converges to the probability of a certain event. It might be better to say experiment. So we repeat our experiment. Our experiment usually tossing a coin, rolling a die, or something like this. If you consider the internet, you can find everything concerning law of large numbers and other theorems in probability theory. For example, you can find visualization of this result. So here, proportion of heads. Excuse me. Start again. So this line is the proportion of heads. First it is 0, then it is 1/2, and so on. So if you toss a coin several times and calculate the proportion of heads, then you find these numbers. The proportion of heads is the relative frequency of heads. It is the same, relative frequency of heads. And you see here it should be close to 1/2 because it is the probability. And the law of large number tells that this line should go to 1/2. 1/2. It is the goal. You see, after 400 trials, it is almost 1/2. Almost 1/2. At the beginning, it is a bit far, and it is random. It is a random sequence. we toss a coin, and randomly head or tail, and calculate the proportion of heads. Always calculate. You see, it is quite close to, it is 1/2, and it is in this narrow place, close to 1/2. You can do it using computer. You can generate random numbers. Random numbers are not really independent. They are so-called quasi-independent. Actually, it is not possible to generate the real experiment using computer. Computer simulation is quite good, very similar to the real life, very similar, but not the same. But for demonstration, it is all right. You can find a lot of demonstration programs for the law of large numbers. For the newcomer, I start again. It is law of large numbers for the proportion of heads. We toss the coin several times, and calculate the proportion of heads. We do it using computer simulation here. And our theorem tells that the proportion of heads goes to the probability of the head. So if you find somehow, somewhere, a coin which is manipulated, then this proportion will go to another number, not 1/2, but the real probability of the head. And using this experiment, you can check if the probability of the head is 1/2 or not. You toss several times the coin, calculate the proportion of heads, and if it is far from 1/2, then the coin should be biased, manipulated. I don't know. What is this? So our next theorem will be this. I will show you something else, but not this. So our next theorem concerns normal distribution. In statistics, normal distribution is very important. It is the basic distribution in statistics. And this result is supported by this. I will tell a few words about this, but a bit later. So I should explain you central limit theorem. Central limit theorem shows us that if you start with any kind of random variables, but they should be independent and with finite variance, and you add those random variables, then the result would be approximately normal. So it is a very interesting and important result. If you start with exponential distribution, you can start with uniform distribution, you can start with Bernoulli or Poisson distribution. Just you add several times, then the result would be approximately normal. Approximately normal. Central limit theorem. let x1, x2, and so on be independent, identically distributed random variables, assume that the variance, their joint variance is finite and positive, and we denote it by sigma squared. It is the variance of xi, and m is the expectation. Then x1 plus xn minus n times n over square root of n times sigma is approximately standard normal if n is large. If n is large. But what is this? It is the standardized version of this sum, because n times n is the expectation of this sum, and square root of n times sigma is the so-called standard deviation, that is the square root of the variance. In other words, x1 plus xn is approximately normally distributed with expectation n times n and variance n times sigma squared. So the sum is approximately normal. And this limit distribution does not depend on the initial distribution of these random variables. They can be, for example, uniform, they can be, of course, normal, they can be uniform, they can be exponential, they can be Poisson, they can be hypergeometric, any distribution. So these random variables can come from any population. This sum is always approximately normal. The only assumption that the variance is finite. It is very important, and this theorem supports then that the statistical observations are usually normal. I will demonstrate this result a bit later, but first I need something concerning statistics. Statistics is based, the theory of statistics, not statistics itself, the theory of statistics is based on probability theory. statistics, we have observations, nothing else but observations. For example, do you like apple? So I like apple, and it is possible to buy apples in the main campus, quite good quality of apples, and I always buy there if it is possible to buy, because it is very nice and cheap. But sometimes the apple is small, sometimes it is large. So, what is your opinion? How can we distinguish two portions of apples? There is a box of apple here, another box here. And your opinion is that, oh, this kind of apple is larger. My opinion is, no, it is larger. How can we decide? You are right, or what I am right. Of course, we should weight the apples, but suppose that there is a large container here, a lot of apples, a large container here. Should we weight all pieces or not? It is possible to take just a sample. These are observations of population. In statistics, population it can mean population of certain animals or plants, but population of for example, cows, or populations of what? Population of certain machines and so on. Population of certain products. Population means just a large set of certain things with the same distribution. So we have apples. For example, first observation is 200 grams, second 250 grams, and so on. Last, say we measure 10 apples, it is 310 grams. These are my apples. Other population, y1 is equal to this, y2 is equal to y10 is equal to this. There are larger, smaller, how to compare. For example, calculate the average. Sample mean or average over empirical mean it is the following. X bar, it is the notation X bar, is x1 plus xn over n. It is the definition. Here it is 200 plus 200 and plus this over 10, and it is, for example, 240. In your case, the average y bar is this. Over 10, and it is 239. Oh, my apples are larger than your apples. But am I right? Might be it is only a random result. Might be. So it is not so easy to decide. The two averages are very close. Very close. Might be the weight is the same in this as in this. The two averages are almost the same. So it is quite difficult to decide if the two averages are the same or not. Of course, in that case, if it is much smaller, then we admit, oh, it is smaller. But the two averages are very close. So we need a theory how to decide in these cases. Just the numbers are not enough. We should know something else about the population. In this case, we usually assume that these apples, the weights of these apples, are normally distributed. And here they are also normally distributed. And if we assume that it is so-called normally distributed population, and it is other normally distributed population, then we have a theory which is called hypothesis testing theory, and we can decide. But in statistics, our decisions always has some possibility that our decision is not true. So we can make certain errors. Sorry to say, the statistical decisions are not possible without any error. So we have always some errors. So I should explain sample-Levi theorem and something concerning the sample. So statistical sample. In the theory of statistics, we have the following definition.